So now let's talk about angularity tolerances. This is our last class of orientation tolerances, but an angularity tolerance establishes control of any flat surface or feature of size at angles other than parallel or other than perpendicular. May also be applied on parallel and perpendicular features. We talked about that before. You know, your angle could be 90 degrees or it could be zero. Um, but that's typically not the way it's done. And it's always referenced to one or more datums. And it's attached with a leader or an extension line from a surface in orthographic views. So let's take a look at how to apply that. Um, Here we got an orthographic view. We have an angularity tolerance here applied to a surface with a leader. The orientation, the actual true orientation would be this 30 degree. It's a basic dimension. So the angle is always defined with basic. And then what we have here is a size dimension that essentially determines what the location of this feature is relative to datum A. So we have a size dimension, we have a basic angle dimension, we have a datum A surface here, and we have our tolerance applied with a leader to our angled surface. Okay, so what does that mean? Okay, here we have that same orientation here for our orthographic view. And so what this does, it creates two parallel planes defining our tolerance. The tolerance is somewhere between this min and max sizes of our locating dimension. And 30 degrees is a basic dimension here, and then our plane fits in between those two. Now, it's based upon what the actual points of the plane are and not based on, well, obviously there's a perfect form at MMC for us, which would be taking this out to the max. But in which case this tolerance zone is actually based on the high spots of where the surface sits now. You can see that from this graph. The 9,000 starts here where it touches the surface at this point, and the rest of this is variation within that zone. So that essentially tells us how this thing is done, and really the feature floats within the size, like I was telling you before. If we were down here at the min dimension, we would still have this 9,000ths based on the high and low spots of the surface. If it's at the max dimension, it's same. It's this 9,000ths parallel planes based on the high and low surfaces of that feature. Now, this is what happens when you have an angularity tolerance on a surface and one datum feature is the reference. The part's constrained in rotation only in the reference datum. The setup maintains specified angles relative to the reference datum, and then dial indicator or other instruments used to measure the orientation. What does that look like? So here is a sketch of how we would actually check this feature control frame here. Angularity, how we would verify the angularity tolerance on a surface, one datum feature referenced. Okay, so in which case we set up datum A with a sine bar such that we get this perfectly at 30 degrees. We set that up using gauge blocks to make sure we get this angle perfectly at 30 degrees. And then once we have that, we will move our indicator over the surface and we check for the full indicator movement cannot exceed this 9,000ths. So that's how we set it up. Let's explore this a little bit deeper. So what if we had an angularity tolerance on a surface with two datums? Okay, in which case that would be this one right here, this one right here. So we got datum B and datum A. In the last example, we had just datum A, but here we got a secondary datum, specified here. That would be on the far side of the surface. So what does that look like when we go to inspect that? Again, it's very similar to what we'd done before. we set the block up at 30 degrees with the sign plate and some gauge blocks, but we also have a second simulator here for datum feature B that we clamp up against the part. So we're further restraining our part to make this check is really what we're doing. Okay, so in the other example where we only referenced one datum, we didn't have that simulator back there that picked up datum B. In this case, we need that simulator to pick up datum B because we're referencing these two datums here. And then we just run the dial indicator over the surface, back and forth and front and back, to make sure that our full indicator movement is less than 9, and that's how we would check that feature for angularity. So what happens when we apply angularity tolerances to a feature's size? This would establish control of a center plane or axis of the feature's size at regardless of feature size. Now, when we're using regardless of feature size, it establishes a center plane or axis. That's just like what we talked about there with perpendicularity before. And then if it's a surface, establishes control of feature surfaces if it's an MMC or LMC. We talked about that before. And the feature control frame adjacent to the size value or attached to the dimension line, that's how we apply it, by putting the feature control frame next to the size dimension or attaching it to a dimension line. And then tolerance zones and datum constraints, they're the same as perpendicularity and parallelism, except that it's some basic angle that's introduced other than 0 or 90 degrees. Okay, let's talk slightly about the tangent plane here. So mating part angles affected by the amount of location and surface variations, and we want to control, the specifying the orientation tolerances applicable to a tangent plane. So the tangent plane symbol follows the tolerance value. So that's how we did it right here. You add that tangent plane symbol. Now, really, what does that mean? Okay. So what we do is we establish a tangent plane based upon our high and low surfaces of the features. That's what that means. And as long as that tangent plane that's established by simulating the high and low features of your surface are within this tolerance zone, then you know you're good. So again, it's just a little bit different. With the other one, we looked at what the high and low spots were relative to that. In this case, we're looking at what the whole tangent plane is and making sure that the whole tangent plane is within that tolerance zone. I'm going to pick up a short movie on the next one. Thank you.